Hello everyone! In this lecture we will continue discussing various server-side vulnerabilities that may be introduced by a web application or server configuration. Let's start with server-side request forgery or SSRF. As the name suggests, it is a vulnerability where a server can be tricked into making arbitrary HTTP requests, potentially returning the HTTP response to the user. Here is an example of vulnerable code. It is vulnerable because the application accepts a user-supplied URL and, without any validation and filtering, fetches the resource and echoes it back to the user. Now, this specific PHP code is also vulnerable to local file access because the file get contents function accepts not only URLs but also file names for reading local files. But let's assume for now that the user can only submit HTTP URLs here. Essentially, this allows an attacker to proxy HTTP requests through the server. At this point, you may ask, why is this a problem? What exactly is the vulnerability here? Can't an attacker just make arbitrary HTTP requests directly from their own browser? So what advantage does it give to an attacker if the server makes the request instead? Well, the key issue is that the server may have access to resources that are not accessible from the outside. For example, the server might be authorized to access sensitive internal resources that an attacker cannot reach directly. So this may lead the attacker to access services running on the server's loopback interface, where internal APIs or admin panels often reside and may not require authentication. Additionally, it lets accessing resources on the local network or firewalled services that only allow connections from the server's IP address. Accessing cloud metadata services is also a common SSRF target. These are special endpoints provided by cloud platforms like Amazon Web Services or Google Cloud. They are exposed at non-routable IP addresses accessible only from within the server itself. These endpoints provide configuration data and instance-specific information without requiring authentication. Here's an example from Amazon AWS. By sending a simple HTTP request to the metadata endpoint, an attacker can retrieve sensitive information like configuration settings and temporary security credentials. These credentials can then be used to escalate privileges or carry out further attacks. To mitigate this, AWS introduced version 2 of the metadata service, where the client must first send an HTTP PUT request to obtain a session token, and then include that token in subsequent requests to access metadata. And this change helps prevent successful SSRF attacks as long as the attacker cannot abuse the SSRF vulnerability to send requests using arbitrary HTTP methods and headers. But okay, here you might wonder, why would a website ever include code like this that lets users trick a server into making arbitrary HTTP requests? One common example is when a website allows file uploads by letting users specify a URL from which to fetch the file. But you can also think of other scenarios where a website implements URL previews, errorless feed imports, or social media embeds. So how can we mitigate SSRF? As for mitigation measures, the application can validate submitted URLs by applying allow lists of accepted schemes, domains, paths, and ports. Unfortunately, enforcing domain restrictions may not always be feasible, especially if the functionality is intended to fetch resources from arbitrary domains. In such cases, one approach is to resolve domains from the submitted URLs and block connections to domains that point to local IP addresses. Consider this example code here. So here we are extracting the domain name from the submitted URL, resolving it to an IP address, and here if it turns out to point to the loopback IP address, we consider it to be an SSRF attack. Otherwise, we proceed to fetch the resource using curl. Very good. Now, the security issue with this code is that it is vulnerable to a DNS rebinding attack. This happens because the DNS lookup performed initially can resolve to one IP address But when the actual connection is made to fetch the resource, the DNS may return a different IP address, potentially pointing to a loopback interface. And this is a classic example of the so-called time of check, time of use race condition. This refers to a vulnerability where there is a window of time between checking the status of a resource and actually using it. And during that window, the resource may change, which in this case allows the attacker to bypass the initial check. To prevent this, we want to make sure that curl connects to the exact same IP address that was verified during the initial check. And we can achieve this by using the curl resolve option, which lets us override DNS resolution by manually specifying the IP address to use for a given domain name and port. So this avoids performing a repeated DNS lookup. In addition, we need to make sure that the HTTP client we use to fetch the resource does not follow HTTP redirects. Otherwise, our check can be easily bypassed by the server redirecting our client to another, potentially internal resource. In curl, we can disable redirects by setting the follower location to false. In the case of curl, this flag is already set to false by default, but that might not be the case for other HTTP clients. And now, this specific check here can still be bypassed in practice because there are actually multiple IP addresses that may point to the loopback interface. In particular, this includes the full range of loopback addresses, the IP version 6 loopback address, and on Linux systems, even the 0 address effectively behaves like the loopback address. So this example nicely highlights the complexity of trying to get things right when relying on a blacklisting approach. Therefore, the most effective way to protect against SSRF attacks is to proxy outbound requests via non-privileged hosts that do not have access to sensitive internal or external resources. So the web application can simply use a proxy server to fetch resources on behalf of users, thereby limiting what can be reached and reducing risk. So that's about SSRF. Let's move on to discuss the processing of untrusted file data, which typically occurs when a web application allows file uploads and performs some form of processing on that arbitrary untrusted data. So here we're not talking just about data storage, but about actively parsing and decoding user-supplied content. This is very risky in general because file formats can be complex and difficult to parse safely without introducing serious vulnerabilities. This means that our web application can become vulnerable due to vulnerabilities in the file parsing libraries that we use. There could be buffer overflows and similar issues, especially if the library is written in a memory unsafe programming language. Then there can be resource exhaustion, denial of service vulnerabilities, and here much depends on how the libraries are used and configured. Image file processing is one of the most common forms of file handling in web applications. Here, the pixel flood type of attack is a specific concern we have to be aware of. In such an attack, an attacker uploads a small image file that claims to have an extremely large resolution. If our library or application does not enforce file resolution limits, then we may run out of memory while trying to decode the image in memory. For instance, if we attempt to convert it to another image format. Then we must also be aware that a valid image file can contain embedded PHP or HTML code. Such code can be hidden inside image metadata using tools like EXIF tool. This will result in a file that passes image format validation, but can still be executed if processed by a PHP interpreter. Therefore, we cannot rely on image validation checks only, but must ensure that uploaded files are never interpreted as executable code and are not served with dangerous content type headers. Then special care is also required when parsing XML files and when processing zip archives. We will discuss the types of attacks related to these two file formats in the next few slides. Let's start with XML files. When parsing XML files, most of the dangers stem from XML entities and how they are handled by XML parsers. The XML standard allows defining custom entities which act like variables containing references to text strings. And here's an example. So here we define an entity called name that contains the string John. Later, when we need the string, we can reference it using the defined entity. In PHP, we can load and parse XML content using the DOM document class. So here we specify the variable that contains the XML content, here the libxml library options, and use save.xml to return the parsed and expanded XML structure. And this will be the result. So here the name entity is replaced with the string John. The first major problem with entity expansion is that it can be abused in resource exhaustion attacks, commonly known as XML bombs. One such attack is the exponential entity expansion attack, also known as the billion laughs attack. Here's how it looks. In this attack, we define a series of entities where each one references the previous entity 10 times. While the initial entity is just a small string, the final entity expanded will contain a billion copies of the string. Parsing this XML structure will take a lot of CPU time and almost 3 GB of memory. Today, this is a well-known attack, and modern parsers attempt to prevent it by limiting the number of times an entity can be referenced. For example, libxml used by PHP will issue a warning if it detects an entity reference loop and will stop expanding the structure. This, however, does not eliminate less efficient forms of XML bombs. For instance, an attacker could still define a very long string here and then reference it here hundreds of times, although these types of attacks are also frequently mitigated by parsers limiting the maximum entity expansion or amplification factor. Anyhow, as you can see, this XML feature can be exploited in denial of service attacks. However, an even more serious issue with XML entities is that the XML standard also supports external entities. And this brings us to XML External Entity or XXE attacks. XML parsers will perform external entity expansion when encountering the system keyword. In such cases, the parser will attempt to fetch the specified file and replace this entity reference with the contents of the file. And this will be the result. As you can see, this allows attackers to read arbitrary files with the system privileges of the XML parser. Note that this works only for text files that do not contain XML special characters, as otherwise the parser will fail to parse it and will return an error. Now, the URL scheme used here is not limited only to local file access. In PHP, any URL style protocol supported by PHP can be used here, which includes HTTP, HTTPS, FTP, and others. This means that external entity expansion can be abused to perform server-side request forgery attacks, forcing the server to make HTTP GET requests to arbitrary resources, and in some cases, even reading back the HTTP responses. But okay, so far we have looked at scenarios where the malicious crafted XML is parsed and its result is echoed back to the attacker, allowing the attacker to see contents of the file or retrieve HTTP responses. What if the parsed result is not returned back to the user? Is it still possible to exploit an XXE vulnerability in such cases? Well, first, we could inject XML that attempts to load a resource from a server controlled by us. This way we can monitor our web server logs to detect whether the target application is making the request, thereby confirming that the parser is vulnerable to XXE. If that is the case, then we can use the blind XXE attack technique to exfiltrate the response. So let's assume a scenario where no response and no error are returned. So here we are parsing an XML with these two library options, and you will see in a moment why this extra option is necessary for the attack to work. This here is the malicious XML that an attacker submits to the parser. What it does is that it defines an external document type definition hosted on the attacker's server. and requests the expansion of an XML entity called send. To expand this entity, the parser will look for its definition in this file hosted by the attacker. This file, in turn, will contain this code, which defines the send entity as an external entity pointing to this URL, where the path of the URL refers to this file entity that is defined as an external entity containing the contents of the file that the attacker wants to exfiltrate. So as a result, the parser will request this URL, leaking the contents of the file to the attacker's server. Now, in practice, however, this will not work for a very simple reason, because this password file contains new lines, which will make the resulting URL invalid. As a workaround here, we can use the PHP-specific PHP scheme, applying base64 encoding on the file contents. This will work as expected. The parser will fetch the external document type definition and will leak base64 encoded contents of the password file. So we had to use the DTD load parameter here to enable loading of the external document type definition here. But alright, what measures can we take to prevent these types of XML entity attacks? The answer is that here we need to figure out how to disable these dangerous XML features in the XML parser that we are using. In the case of libxml, which is used by PHP, the best approach is to deny the loading of XML entities by not passing this no end option. If we do not pass this option, the parser will not try to expand entities, and we will be protected against all the attacks involving XML entities. If we do need to expand entities, then at least we should deny the loading and expansion of external entities by calling this function and passing through here as a parameter. Then we can deny the loading of external document type definitions by omitting this libxml option, although this has no effect if external entities have been disabled altogether. Then it is also important to enforce depth, recursion, and size limits by not passing this option. If we pass this option, then our parser may become vulnerable to trivial XML bombs, although the effectiveness of such attacks depends on the specific version of libxml used. And finally, it is a good idea to suppress error reporting output, since libxml can be very verbose with parsing errors which may leak sensitive information. So these are some of the configuration options available in PHP's libxml library. The challenge here is that there are dozens of different XML parsing libraries out there, and it can be very difficult to determine what defaults are used by each parser and whether these dangerous XML features can be configured or disabled. Even more concerning is that we might not even be aware that the library we are using is parsing XML. For instance, we might use an image processing library that supports also SVG files, which are actually XML files, and thus our application can become exposed to the attacks. To summarize, we must be extremely cautious when passing untrusted user input to any library that might perform XML parsing on that input. Now, if our application accepts and parses zip files, we need to be aware of attacks that can be executed using maliciously crafted zip archives. And this does not only apply to files with a .zip extension, as many common file formats are actually zip archives under the hood. So if our application uses libraries to parse any of these file formats, then it could also be vulnerable to the attacks that we will discuss here. Note that similar attacks may also exist for other archive formats, but we will focus on zip here since it is the most common. So the first attack is called a decompression bomb. The idea here is to have a tiny zip file that expands into a huge file when decompressed. Here's how we can create such a zip bomb using Python's zip file module. So here we are creating a bomb.zip file using the deflated compression method and adding a file bomb that contains 1 GB of the character A. Because the data is highly repetitive, this 1 GB of data compresses down to just about 1 MB. So the resulting zip file is 1,000 times smaller than the data it actually carries. If you open this 1 megabyte zip file, we can see that it holds a 1 gigabyte file inside. So the problem here is that our server might quickly run out of disk space while trying to decompress this kind of zip bomb, or it may run out of memory if it tries to decompress the file in memory. So how can we prevent this kind of resource exhaustion attack? One approach is to check the uncompressed size of files before extracting them. However, the problem is that we cannot trust this value as it is stored in the archive's metadata and therefore can be easily forged. Let's take a look at how this can be done. First, we can use the tool zip_details to find where the uncompressed file size is stored. The tool outputs a lot of details, but we are only interested in the central header uncompressed length field. Here it shows the length encoded in 4 bytes, and here is the offset where it is stored in the zip file. Next, we open the zip file in a hex editor, locate that offset, which will be near the end of the file, and here are the 4 bytes that encode the length. We can modify these bytes to whatever value we want. And after that, it is a good idea to run the zip tool with the -f flag to fix the file, as it synchronizes the uncompressed length between the central and local headers. Without this step, some zip tools might consider the file corrupted. And that's it. Now, how such forged metadata is handled depends on the zip library. Some tools ignore metadata and just decompress all data available in the archive. For example, the archive manager on Ubuntu will decompress everything, but then report a wrong size error and delete the extracted files. The safest approach is to decompress only up to the size specified in the metadata, but not all tools do this. Most libraries, however, provide an option to set a maximum amount of data that the decompressor is allowed to return, and we should definitely use that option if we want to protect against zip bomb attacks. Note that zip bombs can achieve a much higher compression ratio than here in this example. One technique is to create a zip archive with other zip files nested deeply within it. While our application is unlikely to attempt to unzip all the files recursively, antivirus tools that scan entire archives could be vulnerable to this kind of attack. Then, a path traversal vulnerability can occur if we do not properly validate file names of files stored in a zip file. Here's how a malicious zip file can be created. So here we are creating a zip archive that includes a file name containing path traversal sequences. When we extract files from such an archive, these files may not end up in the intended directory, but instead in a location specified by the attacker. In this example, a PHP file containing backdoor code will be written into the server's webroot directory, enabling the attacker to access this file directly through the browser and execute arbitrary system commands on the server. Here's how such a file looks when opened with an archive manager. So we can see a nested directory structure, and after navigating to the deepest level, we will find the malicious file. Then, symlink or symbolic link path traversal is another issue to be aware of. The fact is that the zip file format specification also enables support for storing symbolic links, which are like shortcuts to other files. This is mostly a Linux-specific feature. Here's how we can create a symlink that points to the etc password file. So by accessing symlink.jpg, we will actually access the etc password file. We can add this symlink to a zip archive, upload it to a server, and if the server extracts this file into public web directory, then by accessing this image file, we will be able to read the contents of the etc password file. Note that for this to work, the web server must be configured to follow symlinks, and the web server process must have the permission to read the file to which the symlink points. Also note that symlinks can point not only to files, but also to directories. So by exploiting symlink-based path traversal, it may be possible to trick the server into reading or writing into files or directories to which the symlink points. Here is how such a symlink looks when opened in an archive manager. Now, there's actually nothing in the UI that would indicate that this is not a standard file but a symlink. However, after extracting this file, we would see that it is a symlink. The success of the attack also depends on the tool or library that is used to extract the file, because not all zip libraries apply the special symlink file attributes after extracting the file. So to prevent this attack, we could validate the file attributes before extracting the file. But how to do this depends on the specific library or tool that we use. The final issue, which might be a bit unexpected, is that zip archives can contain multiple files with the same name. Here's an example code of how we can create a zip container with two files that have the same name but different content. And here's how it looks when opened in an archive manager. So due to this, we have to make sure that our code is able to handle duplicate file names without introducing vulnerabilities. For example, our code might validate the first file it encounters, but when extracting, that file will be overwritten by the second file with the same name. So the result would be that we check one file but use another, potentially malicious file. This kind of logic flow is not just limited to zip archives. The same principles apply in any context where the uniqueness of a data identifier is not guaranteed. And therefore, this is a very good place to discuss the HTTP parameter pollution technique, which exploits non-uniqueness in HTTP request parameters. Consider the following HTTP request that contains two identical parameters with different values in them. So here the question is, what will happen when a web application receives such a request? The fact is that there is no standard that prescribes what should be done in such a situation. So how to handle duplicate parameters will depend on the web server and the server-side scripting language. For instance, in PHP, the last parameter wins, so querying param will return value 2 here. In Java servlet pages or JSP, the first parameter wins, so value 1 will be returned. In Microsoft ASP.NET, duplicate parameters will be combined into one comma separated string. The risk here is that if the application uses the first value for validation but the second value for execution, an attacker can trivially bypass the validation. This would happen when an HTTP request is passed through different web application layers that handle such a case differently. So here's an example of potentially vulnerable code. So here, a PHP application checks whether the value inside the parameter is valid and then forwards the entire request to some backend server. The risk here is that this backend server may use the other value passed in the query, which would effectively bypass validation performed by the frontend server. Note that while in this example we're using a GET request, the same applies also to request parameters sent in the body of a POST request. Parameter injection is a somewhat related vulnerability where HTTP parameter pollution could be used to override parameters. Consider the following vulnerable code that constructs query by string concatenation without URL encoding untrusted user input. Here an attacker can inject additional parameters by using the URL encoded ampersand character and the equals character. After receiving it, the server will URL decode the value, and the end result will be this string with an additional action parameter that may override the hard-coded action parameter provided here. The correct approach here is to URL encode untrusted user input when placing it into the URL parameter values, as then special characters encoded and not interpreted as parameter separators. So that's about HTTP parameter pollution. A somewhat related note to add here is that if we add square brackets to the parameter's name, PHP will convert the parameter to an array with the duplicate values inside it. So when querying the param, we will get an array with all values inside it. So it is good to keep in mind that such variable can return not only a string value, but also an array. As the final topic for this lecture, let's look at various information disclosure flaws, which most often occur due to misconfiguration of a web server or web application. The most basic type of information disclosure flaw happens through excessive error reporting, where detailed error messages are displayed to users. PHP is happy to report all kinds of errors and warnings. The problem is that, at a minimum, this leaks the full file system path of the web application, which gives attackers insight into the server's directory structure and may help in executing path traversal attacks. In more extreme cases, stack traces may even reveal sensitive data such as passwords, as in this example, where we can see exposed the MySQL database username and password. Here, the error was triggered because the database server was temporarily unreachable, but it might also be possible for an attacker to trigger errors by submitting user input that is unexpected by the application. In the case of PHP, the displaying of errors can be disabled by setting the display errors variable to off, either using the initset function or directly in the PHP init configuration file. That said, it is still useful to show a generic error message that does not leak any sensitive information, but provides a unique identifier so that support staff can investigate the issue on their side. Automatic directory listing is another common flaw that comes from web server misconfiguration. For example, here we see sensitive data such as backups stored under the web root. So directory listing enables attackers to quickly identify files that are not linked anywhere on the website. In Apache Web Server, directory listing can be disabled in the server's configuration using the options-indexes directive. But even with directory listing disabled, storing sensitive data under the web root is still a vulnerability, as file names of sensitive files can often be guessed. This is especially true for version control systems like Git, where attackers might access version control history by navigating to the .git directory. So if we check our web server log files, we will likely see that there are quite a few requests from bots that are attempting to brute force common sensitive file names, as here trying for different variations of backup files. There is a tool called dirsearch that can automate this process. It comes with a large word list of common directories and files that might not be directly linked on the website. For example, here it identified what appears to be a backup of the index.php file. So the source code download might be possible if there are backup files or temporary files left under the web root directory. To prevent password compromise in such cases, authentication credentials and database connection strings should not be hard-coded into the application, but stored in a separate file, preferably outside the web root. Then there are PHP include files, usually with a .inc extension, where PHP applications commonly store reusable code and configuration. For example, storing database credentials in a config.inc file, and then including that file in other PHP files. So the best practice is to store these include files outside the web root, but if that is not possible, the server should be configured to block direct access to .inc files. And the final thing to mention is to be careful about developer comments left in HTML code, as they can leak information useful to attackers. For instance, there might be debugging information listing to-dos, credentials and access tokens, information revealing software stack used, and so on. So the best approach is to strip all HTML comments before deploying the application to production. Well, alright, here we end the lecture. Thank you for watching.